for
chemistry.
Yeah, baby.
Okay, welcome to Let's Get to the Marks, going through the AQA Chemistry Paper 2 higher tier. This is a 2018 paper for separate science, triple science, or chemistry, GCSE, however you like to call it. Got an hour and 45 minutes. There were 10 questions. Ooh, 100 marks. Let's get into it. This question is about chemicals in fireworks. Colored flames are produced because of the metal ions present in fireworks. What color flame would sodium ions produce? Okay, so this is part of your cation test. Cations are positive ions. Sodium, the way I remember it, sodium is like the color of the sun. Sun, sodium. So I think yellow is going to get you the mark. You probably get away with saying orange as well. So I think sodium, the S stands for sun. Anyway, that's just how I remember the color of the sodium flame. Name a metal ion that would produce a green flame. So there's a number of different ones that could produce a green flame. We could go with copper 2+ ion, but there's a number of other ions that can produce green flames. But on your syllabus or specification for AQA, you just need to know that the copper 2+ ion can do a green or blue flame. Okay, let's move on. There are a number of other green ones, as I say, that they'll have to accept because they do produce a green flame, like barium ions. Right, 1.3. Some fireworks contain a mixture of metal ions. Why is it difficult to identify metal ions from the color of the flame? So this is just the simple fact that if the colors are mixed together, you might get a blend of the two colors. So you might get a blend of the colors, which hides or masks is a good word, masks the real color. So for example, let's say you had a mixture with a red and orange color, it might come out yellow. Or if you had like, I don't know, red and blue, you might get a purple color flame, but actually the ions are copper and say lithium. So they're giving off red and blue, and together those ions form a kind of purple color. Who knows? But there's some blending of the colors when you have a mixture. So that using just what you can observe with your eyes is not good enough to identify individual ions within a mixture. All right, let's move on. Okay, so if we look at 1.4, flame emission spectroscopy is used to identify metal ions in a firework. Figure 1 shows the flame emission spectra of 5 individual metal ions, a flame emission spectrum for a mixture of 2 metal ions. So what do we have here? We have 5 individual metal ions. Calcium ions give off this line spectra. Copper ions give off this one. Potassium ions give off this one, lithium this one, and sodium ions this one. Here is our mixture of 2 metals. And the question is, which 2 metals are in the mixture? And our possible answers for 2 marks are calcium 2+, copper 2+, potassium plus, lithium plus, or sodium plus. What we have to do is go up here, look at the mixture of the 2 metals and see where these lines match. So let's get down to it and see what the correct answer is. You might want to have a go yourself first. Oh my days, why is this not changing color? Oh, that's why. Yeah, whoopee-doo. Okay, so first of all, I'd say, well, look, there's a line here. Where is there a unique? There isn't one for sodium. Ah, there's one here for lithium. Now we might go, is there one for calcium? We might say, oh, look, there's one for calcium there. So maybe it's calcium and not lithium. But then you'd look at the calcium 2+ ion. It also has these lines, and we don't see any here. So that means it's not going to be calcium. It looks like lithium is one of the ions found in our mixture. We can confirm that by saying, look, there's another line here, there's another line here, and then we got these 2 lines, and we go, oh, well, hold on, there aren't these 2 lines in lithium, but they can come from one of the other ions. Let's see what they come from. And so what we're going to do here is say, well, look, we've got these 2 lines in the mixture, and they're also found in sodium. And then we come over here and we say, look, sodium also shares these lines here with the mixture. And so what about these other lines? There's 2 lines there. What could they be for? Well, when we check it out, we'll find that these lines are in lithium. So there's a perfect match between all of these. That line is in lithium and that line is in lithium. But what we find, there's a perfect match between everything in lithium and everything here. Look, there's another one in lithium just there for the calcium band. And so these pink ones all represent lithium, and these. So we can see here, these pink circled bits are from lithium, and these orange circled bits are the unique fingerprint or spectra for sodium. And when we join these two together, we make this perfect mixture of two metal ions, and we can see all the places where the matches are, and they're all covered. So it's definitely sodium ions and lithium ions. And this will get you two fat marks. The compounds in fireworks also contain non-metal ions. A scientist tests a solution of chemicals used in a firework. 1.5, silver nitrate solution and dilute nitric acid are added to the solution. A cream precipitate forms. Which ion is shown to be present by the cream precipitate? Okay, first of all, just want to make a little point. When testing for anions, which is a negative ion, an ion, when you test for anions, we often add acid, like dilute nitric acid is added in this situation. The acid is added to remove impurities like carbonates. They're often removed from acids because obviously when you add an acid to a carbonate, it releases carbon dioxide, it removes the impurity. So silver nitrate solution and dilute nitric acid are added. A cream precipitate forms. So you have to know your stuff here, but this is the halide ion test, and you get three different colors depending on which halide you're dealing with. So if you're dealing with chloride ions, you get a white uh, precipitate. If you're dealing with bromide ions, you get cream. And if you're dealing with iodide ions, you get yellow. So the fact that we have a cream precipitate tells us that bromide ions are present. And you can either write Br minus or you could write bromide ions. You don't get any precipitate, or the precipitate's colorless with fluoride ions. And so we can't identify fluoride ions by this process, but we can identify chloride ions. Another little point to make is the acid you contain, or the acid you use to get rid of impurities, we use dilute nitric acid here, mustn't contain one of the ions you could be testing for. So it would be wrong for us to use hydrochloric acid, because hydrochloric acid would break down into hydrogen ions and release chloride ions. So you definitely wouldn't want to use hydrochloric acid because the chloride ions may tell us that there is a white precipitate there, and they may mask the fact that there's bromide ions there. Anywho, let's move on. That'll get you a mark. All right, moving down. 1.6. Describe a test to show the presence of sulfate ions in the solution. Give the result of the test if there are sulfate ions in the solution. That's worth 3 marks. Why don't you have a go? Okay, I'm going to go through it. So a sulfate ion looks like this. Remember, this is an anion, and I always like to think anion. I like to think of the N as negative, a negative ion. So you're saying the sentence a negative ion. That is an anion. Okay, and that is the sulfate ion looks like that. So we're going to test for that, give the test and the results. Or the first thing we want to do is get rid of impurities. So we want to say add an acid. Now, what acid do you want to add? Why would it be bad to add sulfuric acid? You mustn't add sulfuric acid because, of course, sulfuric acid is going to break down into hydrogen ions and sulfate ions. And that is going to give a positive result. Even if the sulfate ions aren't present, we're going to get positive results. So you don't want to do that. You want to think of something else. So add an acid like HCl, hydrochloric acid. Okay, that will get us 1 mark. The next step is to add barium chloride solution. Now, barium chloride solution can be written like this, Ba, because Ba is a 2+ ion, barium, it's in group 2, chloride, and then solution. And what that does is that's going to split up into barium and chloride ions. And the barium ions are going to react with the sulfate ion like this. What do you think they're going to make? They're going to make barium sulfate. Now, barium sulfate is insoluble. Barium sulfate is what we use in barium meals. It absorbs X-rays because it is a white precipitate that can absorb the X-rays, so it's great for medical imaging. Anywho, it makes this barium sulfate that's white. So the result is a white precipitate of barium sulfate. And here we go. So you're going to get the marks here for saying add an acid, add barium chloride solution, you get a white precipitate. The acid is for getting rid of impurities. Okay, that's the end of question 1. Let's sing on to question 2. Methylated spirit is a useful product made from a mixture of substances. Table 1 shows the mass of the substances in a sample of methylated spirits. You've got ethanol 265.5, methanol 23.3, pyridine 3, and methyl violet 1.5. What is the name given to a useful product such as methylated spirit. Right, so we've got a mixture where the different components have been added in specific or exact amounts. Hopefully you remember what this is called. It's called a formulation. Okay, and that is going to get you a mark. So whenever you have a mixture, so a use where all of the components are useful, have specific uses, and are added in exact amounts, like different amounts. Okay, let's move on. Calculate the percentage mass of methanol in the methylated spirit. Okay, so this is nice and easy. What we want to do is methanol is 23.3. So what is the percentage of it in the total? We want to do 23.3 over the total. So that is going to be, where's my calculator? We're going to need to do 265.5 plus 23.3 plus 3 plus 1.5. If we add that all up together, that equals 293.3, and then we want to times 100. So we want to do 23.3 divided by answer equals that times 100. Bish bash bosh. That equals 7.94%. And that's if we go to 2 decimal places, and that's going to get you 2 marks. Nice. Oh, geez. Putting those damn ticks on again. Random ticking. Methylated spirit contains ethanol and is available cheaply. Methylated spirit also contains pyridine, which has an unpleasant smell, methyl violet, which makes it purple. Suggest why pyridine and methyl violet are added to the ethanol to make methylated spirit. Well, if it's got a nasty smell, it's going to deter, it deters young children from drinking it. Maybe prevents alcoholics from drinking it. Um, the color allows people to identify it. It's got quite a unique color, this bright purple color, and that allows people to identify it, makes it easy to identify. The smell is going to make it easy to identify. It's going to put you off, realize that it's dangerous. It's going to deter young people from drinking it because it smells horrible, because that would be very dangerous for them. And even alcoholics who may be trying to get hold of methylated spirit, which would be very dangerous because it contains such a strong amount of alcohol, the smell and the color will help put them off of it. Hopefully, any one of those will get you a mark. Suggest one use of methylated spirit. Well, it can be used like all alcohols. They're very flammable, so they can be used as a fuel. Now, if you're wondering for some other uses, alcohols are excellent solvents. So we can say used as a solvent. It does contain ethanol and methanol, so they're both alcohols, and they're good as solvents, i.e. dissolving things like nail varnish off your figures, getting paint off paint brushes. So really good solvents like that, but also they're highly flammable, so they burn and they can be used as a fuel. Excusez-moi. 2.5, describe how ethanol is produced from sugar solution. Give the name of this process. So how do we make alcohol from sugar? This is called fermentation. And essentially, you take some glucose, C6H12. All you biologists know this off by heart from photosynthesis reaction and respiration. C6H12O6. This is broken down anaerobically, that means without oxygen, into ethanol and carbon dioxide. So, yeah, what is ethanol? C2H5OH. You can write it like that, or you could write C2H6O plus carbon dioxide. Now that is not balanced, so I would have to balance that up. So we're going to have 2 of these, that makes 4, and then I need 2 more of these, and that makes 6. Okay, so 1 glucose breaks down into 2 ethanol and 2 carbon dioxide. Anywho, we want to explain how this is done. What's the catalyst? There's a microorganism we use here. Hopefully you know what one it is. It's yeast. You don't want to go above 30 degrees, otherwise it starts to denature the enzymes of the yeast. So I'm going to put all the info down, give the name of the process. It is made using yeast as a catalyst for the reaction called fermentation. It is anaerobic without oxygen. They convert glucose into ethanol, and carbon dioxide. And this is great in the food industry. This is how we make bread rise. The alcohol evaporates, so you don't get drunk off the bread. You won't taste the alcohol in the bread, but the sugar in the flour is turned to ethanol, and that evaporates in the oven because it's volatile, has a low boiling point, and the carbon dioxide forms the bubbles in bread, which make it rise. It's also obviously used to make beer and wine and other alcoholic drinks. So this will get us three fat marks. One is really for naming that it's called fermentation. One for saying that glucose, we're using sugar or glucose into ethanol and carbon dioxide, and one for saying it's anaerobic. And I guess there's also one for mentioning yeast. 2.6. Figure 2 shows part of the displayed formula for ethanol. Complete figure 2. So ethanol, eth, means two carbons. Hopefully you know the other ones. Meth is one carbon, prop is three, and bute is four, pent is five. What we need to do, carbon is in group 4 of the periodic table. We need to count how many bonds are around it, then we know it's cool. So 1, 2, 3, 4. That carbon is happy. All 4 electrons are bonded, and that's what you need to be checking. So we need 4 more bonds around this one, and that's the 2 carbons. If it's an ol on the end, it means it has the OH group. So we need to write OH, and then over here, bish, bash. That's all done. Now, oxygen, just for your info, is in group 6. It can only make 2 bonds, therefore, because it can only accept 2 electrons when it's sharing. And hydrogen only has 1 electron and only needs 1 to fill its outer shell. So you can tell it only needs 1 bond. So these are all done, and that is great. Okay, 2.7, name the gas when sodium is added to ethanol. So when you add sodium to ethanol, it releases hydrogen gas. It's the same as when you add sodium to water as to when you add it to ethanol. And methanol was used to produce methanoic acid. What type of substance reacts with methanol to produce methanoic acid? And the answer here is if you want to turn methanol into methanoic acid, you have to add oxygen. So I'll just show you that. Like if you have OH, right? And there is your old methanol. So that's methanol. What we're going to do, we're going to add it using this symbol to represent an oxidizing agent. So the answer is an oxidizing agent. But let me just show you how it becomes methanoic acid. So we want to go bish, bash, bosh. Now, methanoic acid still has an oxygen here, still has the OH group like that, still got the OH group, but it's had an extra oxygen added. Look, there's an extra oxygen. Oh, I need to get rid of one of these hydrogens. Got to do the check. 1, 2, 3, 4, 5, 6. Oh my gosh, how many? I've got 1, 2, 3, 4, 5, 6. I need to get rid of 2 hydrogens here. Boom, boom. There is methanoic acid. You can only have 1 hydrogen attached there. So 2 of these have to break off to allow this oxygen to attach. That is methanoic acid. And so when you remove hydrogen from something or add oxygen, they're both known as oxidation. When you add hydrogen to something or take oxygen away, it's called reduction. So just adding hydrogen can be reduction or taking oxygen away. Here we're both taking hydrogen away and adding oxygen. So it's known as oxidation. And this is an oxidizing agent. It isn't really an oxygen atom. It's something that carries an oxygen atom. And we show it with these brackets, meaning it's an oxidizing agent. And that could be something like potassium dichromate, which is a well-known oxidizing agent used in organic chemistry. So we can just say oxidizing agent. And you would get the answer if you put the symbol for that. So you can just remember that. Or you could even give an example of one and say potassium permanganate, potassium dichromate. So there's a number of different oxidizing agents we could talk about. Okay, that's the end of question 2. Okay, question 3. This question is about gases. Figure 3 shows how nitrogen is used in the Haber process to produce ammonia. So this was a guy called Fritz Haber, and he won the Nobel Peace Prize for this process, which is a really big award in science because with ammonia you can make fertilizers, and he increased world food production by 50%, which ended a lot of starvation. Okay, let's get down to it. Figure 3 shows nitrogen here coming into a reactor, and gas X, unknown gas, also joining the nitrogen in the reactor. They then go through to a condenser, obviously have a reaction in the reactor. Then they go through to a condenser, and any unreacted gases are recycled back in. Very environmental. And the product, ammonia, is taken off from the condenser. So let's zing down and see if we can do these questions. 3.1, gas X in figure 3 is obtained from methane. Name gas X. So you've got to think to yourself, well, methane is CH4, so it must be a gas I can get from this. And it's also a gas that we need to make ammonia. And if we go back up, we might get some other clues. I mean, you should know this off by heart anyway, but if you didn't, you might be able to gather some clues. So we got nitrogen going in and ammonia, NH3, going out. What do we need to make ammonia? Well, we need hydrogen. And that hydrogen, it was telling us, was made from methane, like that. So they took the hydrogen from methane, added it to the nitrogen. Where did the nitrogen come from? The nitrogen just came from the atmosphere or the air. They bang those together in a reaction where you need one of those, three of those, and you make two of those. And this is known as the Haber process. Okay, so our missing gas is nitrogen. Enough of my waffle. Did I say nitrogen? Missing gas is hydrogen. Okay, cool. Give the approximate temperature and pressure used in the reactor. You have to know these off by heart, these numbers. So the temperature we use in the Haber process is 450 degrees, and the atmospheres is 200 ATMS, and that is an abbreviation for atmospheres. So that's 200 times Earth's pressure. On the surface of the Earth, and the temperature is obviously 450. The mixture of gases from the reactor cools in the condenser, suggests why ammonia condenses, but the other gases do not. So why is it that the ammonia comes out and goes back into a liquid from a gas, but nitrogen and hydrogen are still gases and so can be recycled back round? Really cool. So the mixture can be completely separated. And the reason is they have different boiling points. And in fact, ammonia has a higher boiling point. Or it's a bigger molecule. It has bigger intermolecular forces. So that's why it has a higher boiling point. The hydrogen and the nitrogen are smaller molecules than ammonia, and therefore they still remain as a gas because they have lower boiling points. So even when we cool the ammonia, there's still enough energy to overcome their forces, so they still remain as a gas. Anywho, that's the secret, really. They've all got different boiling points. It's actually a type of fractional distillation. Okay, the Earth's early atmosphere was different to the Earth's atmosphere today. Scientists think the Earth's early atmosphere was like the atmosphere found on Venus today. Table 2 shows the amounts of carbon dioxide and oxygen in the atmospheres on Venus and the Earth today. So they think that our early atmosphere was the same as Venus. So lots of carbon dioxide, 96.5% carbon dioxide, zero oxygen. Earth today has 0.04 carbon dioxide, so we've had a massive go down, and oxygen has obviously gone from 0 to 20.95. So this is really an application question. They're telling you that the Earth's atmosphere is like that when it started. So we've got early Earth's atmosphere, late nowadays atmosphere. The percentage of CO2 and oxygen have changed from the Earth's early atmosphere to the Earth's atmosphere today. Explain the processes that led to the changes. Keyword here, they want us to explain the processes that led to the changes. It's worth 6 marks. So this one's not a bad 6 marker, I have to say. So first of all, we want to explain where did the CO2 go, get 3 marks for that, and then why has the oxygen appeared? We should get 3 marks for that. So let's go for it. They specifically are asking us about CO2 and O2. So we want to say, I mean, background info, I guess, carbon dioxide released, whoopsie, from volcanoes in Earth's early atmosphere. However, oxygen was not released from volcanoes. So that explains why there was no oxygen at the start, but there was lots of carbon dioxide because you don't get oxygen coming out of volcanoes. So what happened to all the carbon dioxide? So the carbon dioxide dissolved into the oceans after, whoops. Well, let's put this in a better order. So water vapor from the volcanoes condensed, turned to liquid after the Earth cooled, forming oceans, rivers, and lakes. But that's just long to write all of that. The seas, the oceans, the rivers, and lakes, basically all the surface water on the Earth, massive rain down, and we get all this lovely water, now as liquid on the Earth. Um, Guess what? CO2 dissolves in water really nicely. So a lot of that carbon dioxide, CO2, dissolves into the oceans. Dissolved into the oceans, it formed sedimentary rocks. So a lot of that carbon dioxide is locked up in chalk, sandstone, limestone, and other sedimentary rocks today. So it forms sedimentary rocks. I'm also going to put here, um, it was also used in forming the bones and shells of animals, so of marine animals mainly. So, but all of us, we've got carbon dioxide locked in our bones, but essentially the bones and the shells of lobsters and crabs and things, and whatever early life was on the earth before lobsters and crabs and all those other sea animals, marine life. So basically, the carbon dioxide got locked into bones and shells of animals. It formed rocks. It dissolved into the oceans. Superbulous. What else happened to carbon dioxide? Well, plants evolved and green plants, I should say. Green plants. Um, I mean, technically, before there were green plants, there were lots of green single-celled organisms that had chlorophyll. And what can you do if you're green and you have chlorophyll? You can do photosynthesis. So they evolved and did photosynthesis. Now, because they've done photosynthesis, what does that mean? They absorbed carbon dioxide to make glucose. So during photosynthesis, not only did they absorb the sunlight, but they took carbon dioxide in and turned it into glucose, locked up into those plants' bodies. That's reducing the CO2 in the atmosphere. So some of it's dissolved in the oceans, some of it's gone into bones, some of it's gone into rocks, some of it's gone into plants and algae, and been absorbed to make glucose. When organisms like animals and plants, whoopsie, plants died. Fossilization occurred. Some carbon locked up in fossils and fossil fuels. So essentially, we've got a lot of carbon dioxide locked up in fossil fuels. I think I've done enough waffling about that, and I haven't left any room to write anything about oxygen. Anywho, the green plants that photosynthesis released oxygen, which, yeah, that explains why photosynthesis released oxygen, which increased O2 in atmosphere. And that's really where all the oxygen has come from. It's come from the release it's come from the photosynthesis that the green plants did. They're releasing oxygen into the atmosphere, releasing oxygen into the atmosphere. Great. A nice, easy 6 marks. Ooh, 3.5. One more for this one. Why are scientists not certain about the percentage of each gas in the Earth's early atmosphere? Quite simply, there's not enough evidence. No scientists were there at the time. This happened billions of years ago. It happened billions of years ago. In fact, about 4.5 billion years ago, you might want to put. But if not, it happened billion years ago. No humans were alive. Um, Not much evidence is left, or we need more evidence, that kind of thing. Yeah, we don't have a time machine, so lots of good reasons why. Okay, let's look at question 4. A student investigated the colors in 3 different flowers, A, B, and C. The colors are soluble in ethanol, but are insoluble in water. Ooh, so these colors will not dissolve in water, but they will dissolve in alcohol. This method is used. Crush a flower A, add the alcohol to flower A. Blish, blish, blish. Filter the mixture. Put the spots on the colored filtrate onto the chromatography paper. Boop. Repeat the steps 1 to 4, this time with flowers B and C. Figure 4 shows the apparatus. We've got a lid. We've got a glass beaker, I'm guessing. We've got a chromatography paper or filter paper. It's hanging off the lid. We've got a start line in ink, and we've got water as the solvent. The student made 2 mistakes setting up the apparatus. Give 1 problem caused by each mistake. So I'm going to go through it. The first mistake is they've drawn the start line in ink. Silly billies. So start line in ink. Why is it bad? ink will dissolve in water. You could say ink will run. Basically, the ink is going to dissolve in the water and just spread out and color the water, and it's not going to climb up the paper, and that's really going to mess you up. So that's going to get you 2 fat marks. Let's zing down. To mistake two and the problem caused by mistake two. So there is another problem here, and it's the fact that they're using water. What did they tell us early on? Ooh, the colors are soluble in ethanol, but they're not soluble in water. It's insoluble. This is why we must use a highlighter, people, or circle things as we are reading the stem. This is known as the stem of the question. Really important to circle or highlight in your exam. Okay. That way you won't miss key things like that. So the second mistake is used water, which I can't spell, water, used water as a solvent. Problem caused, colors insoluble in water will not move off the start line, which is really rubbish. You can't identify them or carry out a calculation to work out the RF value, if that's the case. Okay, let's move. 4.2, shrink it down. Now we can see all of the question. Another student set up the apparatus correctly. Figure 5 shows the student's results. Look, for A, there's 1 dot, B, 1 dot, C, 2 dots. Give 2 conclusions you can make about figure 5. Right, there's a whole bunch of conclusions we can make here, but we can say that A and B only contain one color. So A and B made of one color only, as they've only got 1 dot. Or we can say that C is made of 2 colors. So C made of 2 colors, right? Groovy. That's at least 2 marks, but I just want to show you some other things you could have said. We can say that, yeah, all the colors are completely different. Like flower A doesn't contain any of the colors of C or B, and B doesn't contain any of the colors of C, and C doesn't contain any of the colors of A or B. So, none of the flowers contain the same colors. How do I know none of the flowers contain the same colors? Because look, there's no overlap. C goes that far. C's ones go to different distances than B's one and A's one. Anywho, let's zing. 4.3. Color R has an RF value of 0.65. Color A, sorry, I've read that completely wrong. Slap my head. Color A has an RF value of 0.65. Color A moves 3.2 centimeter. Calculate the distance moved by the solvent. Right, you have to know this calculation off by heart, peeps. So what I'm going to do is zing up. They're saying color A has moved that far, and that's its RF value. What's the distance the solvent moved? Well, we have a calculation for this, and it is, you need to know it off by heart. RF value is equal to distance of the solvent, sorry, distance of dot. I know I could have said color, but distance of the dot over distance of solvent. Oh my days, right? So that's the RF value, distance of the dot over distance of the solvent. Once again, full of spelling mistakes. Zero we go. And we have been given the RF value is 0.65 is equal to question mark. We don't know what that is. Actually, we do. That is A, distance of A over the distance of the, no, A moves 3.2. Calculate the distance of the solvent. Oh my gosh, I flopping this one. So we know that A moves 3.2, and we know that this is the solvent distance. So what have I got to do here? Well, if you put this in a triangle, I love to put these in triangles to make these easier to rearrange. So if I was to put that into a triangle, whatever is above the dividing line goes at the top of my magic rearranging triangle, and whatever's underneath goes at the bottom. So that's the RF value times the solvent distance is at the bottom. And so if I want to work out the solvent, I use this line in the middle, which is a divide line. I go 3.2 divided by 0.65. It's going to tell me how far the solvent moved. So we're going to go 3.2 divided by 0.65, and that is going to tell me how far the solvent moved. So let's put that in the old calc. And the solvent has moved 4.923. So equals 4.923. That is how far it's moved. I might want to round that and put that as just 4.9. So it has moved 4.9 centimeter. So essentially what they're saying, for those of you that don't know, that the water moved 4.9 centimeters there. This only moved that much. And that was 0.65 of how far the water moved. But there we go. Coolio. Let's move on. And this will get us 2 marks. Ooh, lovely. Okay, question 5. Sodium thiosulfate solution reacts with dilute hydrochloric acid. The solution becomes cloudy as the reaction takes place. 5.1. The equation for the reaction is sodium thiosulfate plus 2 lots of hydrochloric acid make 2 lots of sodium chloride plus a sulfur dioxide plus a water plus a sulfur. Explain why the solution becomes cloudy. Okay, so what we've got to do here, folks, is explain why it becomes cloudy. Well, let's look at it beforehand. We've got AQ, AQ, and AQ. So it was a solution. These are all group 1, and acid is colorless, and these are group 1 compounds, which are always colorless in solution. Afterwards, we have a colorless solution. We have a gas, which you can't see. We have a liquid water, which you can't see. And we have sulfur. So it must be the presence of this solid that makes it cloudy. So we're going to say the sulfur precipitates, making the solution cloudy. So it's the sulfur that forms a precipitate that makes it cloudy. We might also want to point out the sulfur is a solid, and that is definitely another marking point on the marking scheme. 5.2. Plan an investigation to show how the concentration of sodium thiosulfate solution affects the rate of reaction with dilute hydrochloric acid. Your plan should give valid results. So really we want to look at this and say, what are we going to measure? What's coming off that we can measure? So there's 2 ways we can measure this. We can either measure the cloudiness by measuring the amount of sulfur produced by measuring the cloudiness, or we could somehow collect this sulfur dioxide because it's a gas. You're not really going to be able to measure the amount of water or the amount of sodium chloride aqueous that's produced. So your 2 ways of measuring how fast the reaction is going, or the rate of reaction, is to measure the volume of gas coming off or the cloudiness of the solution. So there's kind of 2 separate methods. I'm going to go for the volume of gas. It's just easier to write up. You can do, if you want to do the cloudiness method, you're going to use the disappearing cross, where you fill a conical flask and as it goes, you set the timer, and when the cross disappears, obviously you press stop, and then you can measure the rate of reaction. I don't want to do that. I want to measure the volume of gas. I just think it's a bit more accurate. So what I'm going to do is use 5 different concentrations of sodium thiosulfate solution. Then I'm going to, let's make this nice and wide. So starting with my first concentration of sodium thiosulfate, I will use a measuring cylinder on a flat surface at eye level, measure out. I could have used a pipette here, so I will measure out, let's say, 15 centimeter cubed of sodium thiosulfate. I will use a water bath to keep the temperature at, let's just make up a number, 25 degrees. So I'm not changing the temperature, so I want to use a water bath to control the temperature. So that's one of my variables to give valid results. One of the other things, so essentially, where have we got to? So what I've done is I've taken a measuring cylinder, I've measured out my sodium thiosulfate for my first concentration I want to test. I'm going to pour it into a beaker, most probably use a water bath. I want to keep it at like 25 degrees. And I've just got sodium thiosulfate in there at the moment, so it's not reacting. I actually should use a conical flask, is ideal for the method I'm going to use, because what I'm going to be doing is I'm going to be connecting this to a gas syringe. So I'm then going to say, connect a gas syringe. Oh, before I connect a gas syringe, I need to add the acid. So now add dilute hydrochloric acid. Use the same volume and concentration for each of the tests and repeats. Okay, so I'm going to use the same concon volume. If you want, you could state a volume and state a concentration. They like that. So I could say 10 centimeter cubed hydrochloric acid. I could say 0.1 mole per decimeter because it says dilute, so we want it nice and weak. So I might want to say 0.1 mole per decimeter of concentration, and I might want to say 10 centimeters of hydrochloric acid or 15 centimeters, whatever. And just keep that the same each time. I want to say quickly connect a gas syringe to measure the volume of gas produced. So this is a nice accurate way to measure the volume of gas produced is using a gas syringe. So I'm really going to be measuring the volume of sulfur dioxide that's given off. What we want to say is let's see. We want to say, let's measure how much, yeah, start a stopwatch because you're going to need to time it because you're doing rate. If ever you're doing an investigation of rate, you need to use time because rate is something divided by time. So start a stopwatch and record the time taken for 10 centimeter cubed of sulfur dioxide gas to be given off. So that's how I'm going to do it. What is the time taken for 10 centimeters of sulfur dioxide gas to be given off? Okay, I'm then going to say repeat 3 times for each concentration of sodium thiosulfate and calculate a mean for each. Then what do I want to do? I want to plot a calculate the rate by dividing the mean volume of gas given off over the time taken. The mean volume of gas is always going to be 10 centimeter cubed over the mean time taken, I should say. The time taken is not going to be, I shouldn't really say the volume because that's going to not be a mean. That's always going to be 10 centimeter cubed in my one. And then I'm going to calculate the mean time taken. We're going to divide that, bish, bash, bosh. That should get me 6 marks. Lovely jubbly. I could then say plot a graph of concentration versus rate of reaction. And that's not concentration of the acid, that's concentration of the sodium thiosulfate. And there we go. That would be my experiment. So the fact that I've given a nice range of concentrations, I've given some technical thing about how to measure out the volumes accurately. I've said I'll use a water bath, so that's a control variable. I've said I'm going to use the same volume and concentration of hydrochloric acid each time. I'm going to try and quickly connect the gas syringe to measure the volume of sulfur dioxide given off. Remember, start a stopwatch and record the time taken for 10 centimeters of gas to be given off. Repeat 3 times for each concentration of sodium thiosulfate and calculate. What I should say is calculate a mean time. A mean time taken for each conc. Okay, calculate the rate by dividing the volume of gas given over the mean time taken. Plot a graph of concentration versus rate of reaction. Great. Uber duper. What we should find is, and our results, it's always good to add in what you might expect to see with your results. As the concentration of the sodium thiosulfate increases, I expect the rate of reaction to increase, the mean time to go down, and therefore the rate of reaction to increase. That was long. Don't you just hate those 6 markers? Okay, Question 6 about polymers. 6.1 polyesters are produced when monomers join together and lose a small molecule. Name the molecule lost. It's in the name. Well, it's not in the name. It's called a water molecule. You could just put H2O. Nice. Longing this out. So water stroke H2O. And that's because it's called a condensation reaction when these guys join together. Polypropene is produced from propene. Complete the structure of polypropene in the equation. Now, this is different. This is called addition polymerization. It's worth 3 marks. It's generous. Right, all you have to do here, there's a method. You draw the lines going outside the brackets. They've done that for us, which is uber generous. You turn this double bond into a single bond, and then you literally just draw everything coming out in the same place. I'm actually going to fall off my chair. I cannot believe that this is 3 marks. That is utterly insane. You're getting a mark for drawing that and a mark for drawing everything else in the same place. And then we want to put an N. Wow, that does not make any sense at all. So carpets are made from polypropene wool, which is a mixture of polypropene and wool, or polypropene wool and a mixture of polypropene and wool. Okay. Polypropene wears out more slowly than wool. A mixture of polypropene and wool to make carpets is more sustainable than using just polypropene or just wool. Suggest why. Okay, this is one of those dreadful questions. Well, polypropene, what is polypropene? Polypropene is a polymer, which is a plastic. So polypropene is non-biodegradable, which means it doesn't break down by itself. So it's going to take up space in landfill sites and stuff like that, or has to be recycled. So has to be recycled or goes to landfill. Okay, no one spells landfill with an E except for me. So that's a nice valid reason as to why if you make it all with plastic or polypropene, it's bad. What else can we say about it? Polypropene comes from hydrocarbons, so is from non-renewable resources, so which will run out. So if we use up all the polypropene, there won't be any left for future generations. So that's not called sustaining it, is it? That's pretty unsustainable. What else can we say? There's loads of things we can say. Wool comes from sheep, which require large areas of land for grazing, feeding, whatever. Do sheep graze? For grazing, feeding, eating. We have to keep the sheep on large areas of land. So this means deforestation. As you've got to clear the land in order for agricultural purposes, haven't you? So there you go. There's some reasons. I'm sure there's plenty of other reasons why using just a fully plastic carpet or a full wool carpet is not very sustainable. Okay, let's zing on. Bada bada bing. Um, Polymer fibers are used to make firefighter uniforms. Table 3 shows the properties of two polymer fibers. So we've got polypropene and polyester. Evaluate the suitability of polypropene and polyester for firefighter uniforms. So what you want to do here is say positive and negative about both. And I always like to give my final opinion on the end as well. It's just what I like to do with evaluate. So I'm going to look at it and say, well, first of all, polypropene is lighter. Polypropene is less dense, so lighter, easier to wear for firefighters. So it's easier to wear, it's lighter. That's a factor, right? However, polyester has the higher melting point, so is safer for the firefighters. So, i.e., they're less likely to get burnt if they wear the polyester. So that's some other marks. Flame resistance is poor of polypropylene. It also has the better flame resistance. Oh, you got to go for polypropylene, right? It might be heavier and make you sweat a bit, but it's got a higher melting point and has better flame resistance. So we'll protect I'm explaining what that means. So we'll protect the firefighters from getting burnt. Okay, so that's the good thing about that. And then water absorption, low, high. Oh, that's not good. Absorbs lots of water. So yeah, um, however, it absorbs water, which will make it even heavier. So it's going to be uncomfortable. So my vote here would be the polyester is going to be uncomfortable as it's heavy and got low water and high water absorption. So it absorbs lots of water, which you're going to be spraying water around as a firefighter trying to put fires out. And your costume's going to get really, your uniform's going to get really heavy and it's uncomfortable to wear because it's more dense. But at the end of the day, it's better because it's safer. And that would be my final point, which I don't have room to make, but you should have room to write down. So there we go. Bish bash bosh. Okie dokie. Okay, question 7. Older cars are tested each year to measure the amount of pollutants contained in exhaust fumes. Table 4 shows the maximum allowed percentages of exhaust pollutants for petrol cars. We've got the age in years, for example, 16 to 24 years or 3 to 16 years. We've got the amount of carbon monoxide and the amount of unburned hydrocarbons. Okay, let's scroll down. Explain how carbon monoxide is produced when petrol is burned in car engines. Well, what happens is your petrol, whatever it is, it's a hydrocarbon, normally probably something closer to C8, but petrol is a mixture of different chain length hydrocarbons. When it's burnt in oxygen, but there isn't enough oxygen, we will end up forming carbon monoxide because it only has one oxygen and water. And the problem with carbon monoxide is that it is poisonous. But let's get into how it's formed. So, insufficient oxygen, you could just say a lack of oxygen, not enough oxygen. Um, so, incomplete combustion, which means it doesn't burn fully. You normally get a blacker, darker smoke and a more yellow flame when you have incomplete combustion taking place. There's some observations you would make, but these are the marking points. Less oxygen, so incomplete combustion. Now, if I scroll down, 7.2 suggests 2 reasons why the maximum allowed percentage of carbon monoxide has been decreased for newer cars. So what's the bad thing about carbon monoxide? Which is essentially stopping our red blood cells from picking up oxygen and transferring it around the body. And of course, um, so reducing CO2 emissions will reduce health problems and deaths from CO poisoning. There are, woohoo, there are more cars on the road, so stricter limits are needed, i.e., as there are more cars on the road, in order to prevent the total amount of CO in the atmosphere increasing, we have to make the limit of carbon monoxide emission per car more. So we need stricter limits because there's more cars on the road. Okay, that was a bit long, but these kind of points are important. Okay. Give one reason for having a maximum allowed percentage of unburned hydrocarbons in exhaust fumes. So what's the problem with unburnt hydrocarbons? Well, you get something called particulates. What that means is where you've got the sun shining down on the earth, if you get particulates in the way, which are unburnt bits of hydrocarbon, we get something called global dimming. And global dimming means that a smaller percentage of sunlight reaches the earth. And so we call that global dimming. Basically, it gets darker, you're going to get less photosynthesis and all of that kind of stuff. So unburned hydrocarbons cause global dimming. Now, if you didn't think of that, you could also have said um, to reduce respiratory problems. So unburnt particles, hydrocarbons in city centres and places you breathe in, they cause breathing problems, asthma and other sorts of breathing problems. Okay, let's move on. Oxides of nitrogen are also pollutants contained in exhaust fumes. Describe how oxides of nitrogen are produced when petrol is burned in cars. So essentially, this is what happens. I just got to change my color on that. 1 second, peeps. So here's our car driving along the road. Now, inside the engine, what happens is nitrogen and oxygen from the air, from the atmosphere, enter the car engine and they come out of the exhaust as nitrogen oxide or nitrogen dioxide. So, um, and that is dodgy. Describe how the oxides of nitrogen are produced in petrol when petrol is burning car engines. So essentially, oxygen and nitrogen, they're not coming from the actual petrol. The petrol is made of carbon and hydrogen. Notice nitrogen dioxide has nothing to do with the carbon and hydrogen in the hydrocarbon that petrol is. So the oxygen and nitrogen are actually happening separately, not to do with the burning of petrol. So what we want to say is the car engine, when it's burning petrol, gets very hot. Better to say, end up with a high temperature. So you get very high temperatures, you're talking hundreds of degrees on the metal in car engines. And then nitrogen from the air and oxygen from the air react on the surface of the hot car engine. It almost acts as a catalyst for them, um, combining them to form nitrogen oxides. So what are the key points here? Because I've waffled a little bit there in my answer, but the key points are that you have high temperatures in the car engine and that nitrogen from the air and oxygen from the air react. And those are the 2 points. Anything else is just extra whiffle waffle. Catalytic converters are fitted to the car exhausts to reduce the amount of pollutants released in the atmosphere. Nitrogen dioxide is an oxide of nitrogen. Nitrogen dioxide reacts to produce nitrogen and oxygen in catalytic converters. Complete the equation for this reaction. The equation should be balanced. So what they're on about here is we talked about that problem of nitrogen and oxygen joining on car engines where you can fit something called a catalytic converter. And as those nitrogen oxides are formed, they enter this catalytic converter, which normally has a precious metal like platinum in a mesh in the middle, and then they can react and be broken back into nitrogen and oxygen and sent back into the atmosphere. And what we're being asked to do here, so in goes our nitrogen dioxide or nitrogen monoxide or nitrogen trioxide, and it ends up coming out of the catalytic converter as nitrogen and oxygen. So what we need to do is turn this back into nitrogen and plus something oxygen. So what we've got to do is work out our formula here. Well, we've only got one nitrogen atom on the left of this arrow and nitrogen's diatomic, so we need two. So we're going to put a big fat 2 there. That's going to make 2 nitrogens, so that is all happy. But 2 times O2 is 4 oxygens, so I need a 2 there. And that is going to get us 2 marks. 1 for writing N2 there, and 1 for the correct balancing of putting the 2 2s. Case 7.6, give 2 effects of atmospheric pollution which are reduced by using catalytic converters. So 2 effects of atmospheric pollution. Well, basically they're asking you what are 2 problems caused by nitrogen oxides. So reduction in respiratory problems. Why is that? Well, nitrogen dioxides cause respiratory problems. So you're going to have a reduction in respiratory problems. But also, what do nitrogen dioxides do? Well, the second problem with nitrogen dioxides is that nitrogen dioxides go up, not just dioxide, trioxide or monoxide, they go up into the clouds and they cause HNO3 to form with water, which is acid rain. And then, of course, that rains down and destroys crops, destroys trees, changes the pH of soil and the pH of lake water, killing fish and things like that. So we're going to say reduction in acid rain, and that will get us 2 benefits of reducing atmospheric pollution by nitrogen oxides with the use of a catalytic converter. Okay, let's go down. The catalyst in catalytic converters is a mixture of three elements. Where in the periodic table are these elements most likely to be found? Alkali metals? Well, if we think about the alkali metals, they're very reactive. When they react with water, some of them catch alight, or the hydrogen release catches on fire. They produce hydrogen gas, which is explosive, and they produce alkaline solutions of a very high pH, which would be corrosive. So they would be a bad choice. Halogens, again, halogens are mostly gases and stuff at room temperature and liquids. Yeah, you're not going to make a catalytic converter using halogens. The noble gases are very unreactive, and yeah, they're gases. Again, you're not going to make a catalytic converter out of gases. It's actually the transition metals, that part of the periodic table. If you remember the periodic table, you got that bit in the middle. That is the most crusty periodic table ever. But the transition metals are found here. Uh, X marks the spot. They're found right there. And the transition metals make really good catalysts. So that's the bit of knowledge you should have known, that transition metals make great catalysts. It's because they can have multiple oxidation states. God, I lost the ability to speak. And that means they can be like, or ionic states, or ionic charges. So that ion can be +2 or +3. So it can be reduced or oxidized. Okay, let's move on. A student investigated how temperature affects the rate of reaction between magnesium carbonate and dilute hydrochloric acid. This is the method they used. Heat the hydrochloric acid to 30 degrees in a conical flask. Add magnesium carbonate powder to the conical flask. Measure the loss in the mass of the flask and contents every 20 seconds for 140 seconds. Repeat steps 1 to 3 with hydrochloric acid heated to 50 degrees. Explain why the contents of the conical flask lose mass. So why does the conical flask lose mass? What we have to look through here, we've got a reaction between magnesium carbonate and hydrochloric acid. So if you know about your acid and carbonate reactions, what's going to be released? Let's have a little look. If we have MgCO3, you should know this off by heart. Not necessarily this equation, but you should know the carbonate reactions. Carbonates make a salt, so it's going to be magnesium chloride. They're going to make water, and they're going to produce carbon dioxide. What's special about carbon dioxide? If we wrote the state symbols, carbon dioxide is a gas. So why will the contents of the flask lose mass? We can say CO2 is formed, 1 mark. It is a gas, it escapes. So there we go. That, and of course, gases have mass. They're made of atoms. Why wouldn't they? 8.2, table 5 shows the student's results for hydrochloric acid at 30 degrees. So we've got time, and then we've got how much mass has been lost. We can see that as the time has increased, the mass loss has too. Let's find out what the question is. Plot the data from table 5 on figure 6 and draw a line of best fit. So let's go ahead and do that. Let's have a quick look at the data. Okay, so we're going to go ahead and put this data onto the graph. Here we are. What else do they ask us afterwards? No, do they ask us for a line of best fit? Yeah, draw a line of best fit. How many marks? 3 marks. So the reason why it's only 3, and often graph questions are 4 or 5 marks, in this situation, they've already written the scale for us and they've already labeled the axis. So we're getting 3 marks for just putting the points on and drawing a line of best fit, which is pretty generous when you think about it. So let's get on. There's a point at 0, 0. Whoopsie, my alarm went off. Then we've got a point at 20 and 0.26. So I have to work out how much each one of these squares is worth. You see there's 25 is the value and there's 5 squares. So each square is worth 25 over 5. Each square is worth 5 down here. So that means if I want to go along to 20, I go 4 across. And then I go, that's great. And then what we want to do, that's the time in seconds. I want to go up to 0.26. And the difference here is that each one of these is worth 0.10, but then it's 5 squares again, so I've got to divide by 5, so it's 0.02 for each one of these squares. So if I want to get to 0.26, I need to go 3 up there, and right there is where we're going. 20 seconds across, and 0.26 is there. And then I want to go to 40. So I am going 30, 35, 40, and we're going up to 48. 48 is going to be 4 up. So right here. Okay, that's a pretty rubbish circle. And then we want to go 60. So 60 is there. We want to go to 67. So 67 is going to kind of be 3 and a bit up. So 67, 3.5. Oh, yeah, that's quite hard. And then we want to go to 80. So 80 is there. And we want to go to 0.82. So just one above there. And then we want to go to 100 as the time in seconds. So over here. And we want to go to 0.91. So that's halfway there. And then we're doing 120. So that's one back from here. And that is up to a loss in grams of 0.91. Ooh, that doesn't make sense. Wait, 120 is 0.96. Sorry, I can't read. That's 125, right? Let's take that off. That should be 1 over there. Seems a bit close, doesn't it? Well, we've got 100 to 120, and that was 86. No, that was 80. 80 to 100. Yeah, that's normal. 120. And then another 4, we're going to 140. So 3 along here is 140, and we're going up to 90, 0.99. So there. Okay, now we need a line of best fit. We can see from this we have a natural curve. So all you do with a natural curve, you don't take your pen off, or you shouldn't take your pen off. So there's me screwed. Let's go back again. And then we go up like this. Got to long this out. That's not too bad, actually. He says, nearly perfect. There we go. Line of best fit. So we're going to get 3 marks for that. Didn't take my pen off the whole time. And you're going to get 1 mark for the line and 2 marks for the plots. You're allowed a half square out on any plot, and I haven't been. So we're going to get all 3 marks. Nice. Now, let's move down. Figure 7 shows the results for hydrochloric acid at 50 degrees. Determine the rate of reaction at 50 degrees when the loss of mass is 0.95. Show you're working on figure 7. Give your answer to 2 significant figures. So what we do here is we go to 50 degrees and 0.95, and we want to determine the rate of reaction to 2 significant figures. So I've even already forgotten those digits. There we go. 50 degrees. So what I want to do is I want to come to 50 degrees and determine the rate of reaction at 50 degrees. So that's 50 seconds. This is mass loss 0.95. So 0.95 is bang smack in the middle there. I'm going to 50 seconds, nothing to do with that. This whole line is at 50 degrees. So we want to go to a 0.95, which is bang smack in between 0.9 and 1. So we're going halfway between this square, and we're going to draw across here, and we're going to make a little circle right here, okay? That is going to be our first mark for doing that. We want to determine the rate of reaction at that point. What we need to do when it's a curved line, you have to draw a tangent to the line. Now, a tangent is a straight line, and you want to draw it touching this axis and touching this axis. You want to make sure the space in between the line and the curve is roughly even on both sides. So I'm going to go something like that. That was rubbish. So let's try that again. Yeah, let's go. How's that looking? It's looking okay. Right, so you can see, look, there's the space there is it even to the space there? Yeah, maybe not, but whatever. Okay, so there's my line. Now what you want to do, you're going to draw a triangle here, okay? And we're going to do the axis. We're going to do the Y over the change in X. You can pick any 2 digits, but I like to pick 2, which are nice. So let's go to 100, because that's always nice, and start my line there. And then I'm going to go back down here to 50, because guess what? If I make a triangle like that, that's the top of my little tangent triangle, then that's really easy, isn't it? 100 minus 50. And then I'm going to draw down here. You're never going to get both of them perfect, so this one is slightly harder to work out. It'd be nice if it was a straight line, wouldn't it? Okay, so let's do my readings. I've got X and I've got Y. And what you want to do for a tangent is change in Y over the change in X. So change in Y divided by change in X. Okay, and that is going to give me my rate, my gradient. Well, it's really going to give me my gradient, which is going to be equivalent to my rate. Okay, so let's do that. So my change in X is nice and easy because I'm doing 100 minus 50. Let's have a look what my change in Y is. So that's at 1, and that is going down to there, which is 0.86. So I'm going to do 1 minus 0.86. It should have been 1.00, but there we go. So let's try that on for size and see what we get. So I'm really looking at doing 0.14. Oh my God, how crap is that? Over 50. And my rate is going to be 2.8 times 10 to the minus 3 is what I've got. 2.8 times 10 to the minus 3. And that is going to be in my loss in grams per second. So that's grams per second. And that is my rate. Okay, this question's about methanol. 9.1, methanol is broken down in the body during digestion. What type of substance acts as a catalyst in this process? So methanol has the formula CH3OH, and it's broken down in our body during digestion. So it's an alcohol. What type of substance do you think acts as a catalyst? Is it an amino acid, an enzyme, an ester, or a nucleotide? Which of these do you know is a catalyst in biology, or a biological catalyst? Hopefully, you know, it's going to be an enzyme. Super. Something not to forget is that enzymes are actually made of protein, so they will contain amino acids. All enzymes, or most enzymes, are actually proteins. In industry, methanol is produced by reacting carbon monoxide with hydrogen. Here's the equation for the reaction. CO gas plus 2H2 gas, reversible symbol, goes to CH3OH gas. How many moles of carbon monoxide react completely with 4 times 10 to the 3 moles of hydrogen? So this all sounds rather complicated, but whenever you're given one of these equations, the whole purpose of this is for you to be able to see how many moles of each thing you've got. And what you can do is work out the ratio. So if I have 1 carbon monoxide, it will react exactly with 2 hydrogen. Hence, this 2 here, known as a coefficient, tells us that. And if I have 1 lot of carbon dioxide, it will make 1 lot of methanol, and 2 lots of hydrogen make 1 lot of methanol. So this is the ratio of all the substances in the equation. So how many moles of carbon monoxide react completely with that much hydrogen? Well, the ratio of hydrogen to carbon monoxide is 2 to 1. So I just need to take 4.0 times 10 to the 3, which is the same as saying 4,000, and I need to divide it by 2. And if I do that, I'm going to get 2 times 10 to the 3, and that's this answer right there. So we're dividing it by 2 because you need double the amount of hydrogen to carbon monoxide. So I would need twice as much hydrogen to completely react with carbon monoxide. So I've only got half the amount of carbon monoxide. So that's why, because the ratio is 2 to 1. God, I longed that one out, didn't I? Right, let's move on. 9.3. The reaction is carried out at a temperature of 250 degrees and a pressure of 100 atmospheres. The forward reaction is exothermic. Explain what happens to the yield of methanol if a temperature higher. So basically, if they increase the temperature more than 250, what would happen to the amount of methanol we use? And it's 2 marks. I'm going to go up to the equation and explain it. So you might want to have a think about what would happen. They told us that this reaction was exothermic. And what that means is that the right-hand side of the reaction releases energy. I think of this side of the reaction as the hot side of the reaction. And that means that the left side or the backward side is endothermic. And I think of that as cold. But you don't want to use the words hot or cold in your answer because it's not very scientific, but it just helps me visualize. So if you make this reaction hot by increasing the temperature, and they told us that they increase the temperature, which direction will the reaction go? Well, there was a dude called Le Chatelier, or Le Chatelier, however you want to pronounce his name, and he said that reversible reactions, that's reactions with this symbol in the middle, reversible reactions always move the equilibrium in the direction to oppose or counter your change. So if I make the reaction hotter by increasing the temp, the reaction will try and do the opposite. So it wants to move to the cold side or the endothermic side. And this means we're going to produce more carbon monoxide and hydrogen, and we're going to make less methanol. And that means we will get a decreased or a lower yield of methanol. So let's put that down as our answer. So the forward reaction is endothermic. Explain what happens to the yield of methanol. So we get 1 mark for saying it decreases, less methanol produced. I didn't need to have to write that, but I could just say the yield decreases, which is the same as saying less methanol produced. Why? And it's because the equilibrium shifts to the left-hand side. Now, you don't have to say left-hand side. You can say backwards. And why does it shift backwards? Because this is an exothermic reaction and you've increased the temperature, so it's going to shift to the an increase. I'm just going over and above board here, but an increase in temperature shifts the equilibrium in the endothermic direction. So, and that is backwards in this case, right? Because it's an exothermic reaction, which means the exothermic or the hot side is on the right. So if you increase the temperature, it's going to do the opposite. The reaction will try and do the opposite by shifting the equilibrium in the backwards endothermic side to this reaction. Cool. Let's move on. Oh, get rid of the ticks. Moving down. 9.4, a pressure of 100 atmospheres is used instead of atmospheric pressure. That means that's 100 times the atmospheric pressure. The higher pressure gives a greater yield of methanol and increases the rate of reaction. Explain why. Two-parter. Right, let's first of all look why it increases the yield. So I'm going to zoom in a little. Bosh. Right, how many gas molecules are on the backwards or the left-hand side? We've got 1 carbon monoxide, 2 hydrogen, so I've got 3 Gs. Yeah. And on the right, I've got 1 G. So if I use a high pressure, what's going to happen is Le Chatelier says the reaction is going to try and do the opposite. So if you increase the pressure, what direction is going to decrease the pressure back down? So if you make the pressure higher, the reaction is going to shift to the side with the least gas molecules. So it's going to shift to the right-hand side. And luckily for us, that is going to increase the amount of methanol being made, which is what we want. So we can actually manipulate reactions to give us the best yield to make the most money. So one of the ways is higher pressure shifts the reaction. I should say equilibrium, it's just better language. So shifts the equilibrium to the side with the least gas molecules. In this reaction, it is to the right. So it's shifting the reaction or the equilibrium to the right, and the right-hand side means we make more molecules. This means we get a higher yield, yield of methanol, as methanol is on the right. So the reaction is shifting to the right, and that's the side with the methanol. Why does it shift to the right? Because there's less gas. You increase the pressure. The reaction tries to do the opposite by Le Chatelier's principle. Now, this second bit is not about Le Chatelier's principle. It's a different topic, and they often do this. They mix Le Chatelier's with a different topic. This is the rate of reaction topic. And if you increase the pressure, this is to do with your particle theory. So increasing pressure increases the number of particles in the same space or volume. So we're going to end up with more particles in the same space. And if you have more particles in the same space, you're going to get an increased frequency of collisions. And then we can say more successful collisions, so higher rate of reaction. Now, really, I only needed to say two things for each of these. So I could have just said increasing the pressure means we've got more particles in the same volume, increased frequency of collisions, higher rate of reaction. Yeah, I kind of want to say all of them really for my explanation. But I reckon if you said increased frequency of collisions, higher rate of reaction, you get the 2 marks. But I'm just explaining why there are more collisions, and it's because there's more particles in the same space. And over here, it shifts to the side with the least gas molecules. An increase in pressure will, by Le Chatelier's principle, will try and decrease the pressure, try and do the opposite. If you increase the pressure, what's to decrease it? So it shifts to the side with less gas, so there'll be less particles colliding, and that will give us a higher yield of methanol. So we get a higher yield of methanol and a higher rate of reaction. So actually increasing the pressure is actually super spondopoli suspendus, whatever that means. Okay, a catalyst is used in the reaction to produce methanol from carbon monoxide and hydrogen. Explain how a catalyst increases the rate of reaction. There are two things we can say here. It lowers the activation energy. Now, that's kind of like everybody can memorize that. And this is the bit that confuses people by providing an alternative route. And I'm not going to explain about that because it's only GCSE. You just need to memorize that. So basically, the catalyst allows a different pathway to get from the reactants to the products, and that pathway uses a lower amount of energy. So that's what a catalyst does. Okay. 9.6 suggests why a catalyst is used in this industrial process. Do not give terms of increasing the rate of reaction. So what's another thing you know about a catalyst? And industry means, there's money involved. You're trying to make a profit, right? Industry tries to make money by selling stuff. So why use a catalyst? Because it can be recycled. It doesn't get used up. So it does not, I can't spell, does not get used up. So it can be recycled. Saves money. That's just one thing I could have gone down. I could have also gone down the route of it lowers activation energy. So lower temperatures are needed. It saves on energy. So it's kind of more green for the environment. We're going to use less energy because we can use a lower temperature, and that will save money as well. So there's lots of different routes we could have attacked this at. It can be recycled, so you don't need to replace it. It saves money. Because it lowers the amount of energy used, it's more green, there's less carbon dioxide released. When you try to get a high temperature, you tend to burn fossil fuels and use up non-renewables and release carbon dioxide. And if you're using catalysts, you don't need as high a temperature for your reactions because they lower the activation energy, so you can save on energy and all of that rubbish. Suggest the effect of using a catalyst on the equilibrium of methanol. Well, actually, catalysts always increase the rate of reaction, but this question is asking us about equilibrium. And catalysts have no effect on the equilibrium position. Why? Why, you ask? Because they increase both the rate, they increase the speed or the rate of both the forwards and backwards reaction. So both reactions happen faster. They lower the activation energy for both directions. So you actually do produce your products faster. Um, However, you don't change the direction of the equilibrium because both reactions are favored equally. Cool. Right, let's get on and do the last question, which is question 10. Oh my good gosh. Disposable cups are made of coated paper or polystyrene. Table 6 shows the information on the life cycle assessments or LCAs of disposable cups. So we've got coated paper cups and we've got polystyrene cups. We can see the raw materials are wood for the paper, crude oil for the polystyrene. So we've got a renewable resource with wood. You can plant more trees, right? And we've got crude oil, which is non-renewable. Once you've drilled it out the ground and used it, it's going to take hundreds of millions of years to reform. So actually, in terms of human species life expectancy, it's non-renewable. The mass of one cup is 8.3 if it's made of paper, and it's 1.9 if made of polystyrene. So you can store and transport a lot easier because they're lighter. The energy to produce one cup is 550 for the paper and 200 for the polystyrene. So you could argue that you're using over double the energy to make the paper cups, and that energy often comes from burning fossil fuels. So that using non-renewables essentially could be the situation. The energy released when one cup is burned is 166. So actually we get some of that energy back when we burn paper, although burning does produce pollution. And when we burn plastic cups, you're probably going to get worse pollutants from burning the plastic. But and also it doesn't release as much energy, so you're not getting as much energy in payback. And then the paper is biodegradable, the plastic isn't. The paper is not recyclable. You can't really use paper cups again. They go soggy and mashed. Anyone who's tried to drink a milkshake through a paper straw knows how absolutely useless they are. And polystyrene cups, yes, you can use your plastic cups again and again and again. You just got to give them a little wash. So there's good things and bad things about both of these instruments or utilities or utensils or whatever we want to call them. You can guess the question we're going to get right. We're going to have to evaluate which is better to use. 6 marks, or it might be a 4 marker. They kind of vary sometimes. Oh, it's a 6 marker. Evaluate the use of the coated paper compared with the polystyrene to make disposable cups. Use your knowledge and understanding of LCAs. So really, all of those things I've discussed, you want to talk about. So you kind of want to say what's good and bad about each one. It's better to kind of go back and forward with it. So consider the fact that wood's renewable, the fact that crude oil is non-renewable, and kind of go down each of those aspects, like so raw materials, the mass, the energy to produce, the energy released when you burn it, and all of that. Compare them and then come up with your final answer, which is your opinion backed up by a statement as to which one you think is best. Okay, and I'm going to put your answer right here. So check that out. That's going to get you all the marks. Okay, moving on. 10.2, calculate the energy needed to produce 1 kilogram of coated paper cups. Use table 6, give your answer in standard form. So we want how many kilojoules of energy to make a kilo of paper cups. All we got to do here is say, look, the mass of 1 gram, the mass of 1 cup in grams. So 1 cup is 8.3 grams. We want to make a kilo, and we want to find out how much energy to produce it. So it's 550 kilojoules for 1 cup. So, but how many cups can you make if you have a kilo? Well, a kilo is 1,000 grams. So I want to do 1,000 grams over 8.3 grams. And that tells me how many cups you've got in 1,000 grams of cups. So how many cups have we got? Divided by 8.3. I hope it was the paper cups and not the old plastic ones. So you can get 120.48 cups If you had 1,000 grams of cups, that's 120.48. Sups, I meant to say cups. How much energy does each cup use? Each cup is 550. So I want to times that by 550 to get the total energy in kilojoules. And they're in kilojoules, so I don't need to do any conversions. So total energy is equivalent to 66,265. So we're looking at 66,000. 265 kilojoules. Now, I just needed to check whether I need to round that up to 266 or 264. No, it's 265.0. So yeah, 66,265 kilojoules, and that is going to get you your both your marks. Ooh, no, it's not going to get us both our marks because, peeps, I need to put this into standard form. So standard form, guys. That means I need to do like 6.6 times 10 to the blah, blah, blah. So let's do, what is that? 6.6 times 10 to the 4. Let's have a little look if that is right. I mean, if I want, can I do, I could go 6.625 times 10 to the 4. And if you want to check, is that right? Put what you've just written in. So I want to put 6.625, then press your times 10, and then to the 4, and then press equals. And if it equals 66,000, oh no, I've written that wrong, haven't I? Look at me, what a plum. That should be 6 point, ah, yeah, 6.6 is fine, but then this should be 265 times 10 to the 4. Okay, so, and then you can check that out by putting it in 6.6, 265, press your times 10 on your calculator, put a 4 in next, whack it in there, equals, and you get the correct answer. So this is the correct answer. Always check to your power, always check it out. If you slam that in your calculator and then put equals, it should go back to that, and that will mean you got the right answer when you change to standard form. I'm ticking everywhere. All right, let's move on. Melamine is a polymer used to make non-disposable cups. Melamine, I should say melamine, it looks like amine. Melamine does not melt when it is heated. Explain why. So, polymers normally melt when heated. What are you breaking? Well, just to explain, polymers, this is very rough, but these circles here are supposed to be the different units of a polymer, and then we've got the covalent bond in between the polymers. So that's one polymer chain. Here we've got another polymer chain. When you want to melt a polymer, like a plastic, you want to turn it into a liquid, you have to overcome the cross links. These are the intermolecular forces between simple covalent molecules. Polymers are technically very large, simple covalent molecules because they might be made of 1,000 atoms. One grain of diamond has got trillions of atoms in it. So those are giant covalent or giant ionic or giant metallic. These are still simple. They're still only made of thousands of atoms joined together, but they have weak intermolecular forces. Obviously, what can we extrapolate, or what can we interpret about melamine's intermolecular forces? It must have quite strong intermolecular forces if it doesn't get melted when heated. So I'm going to say melamine, it's still a simple molecule, but I'm going to say melamine has strong intermolecular forces between the polymer chains or strong crosslinks. They require lots of energy to overcome or break. Now, when it says it doesn't melt, of course it melts. All things melt or sublime. You can melt anything. It's just saying when it's heated, it's not easy to melt. And that's so lots of energy is needed to break the strong intermolecular forces between the layers, or the strong crosslinks between the layers, or the lots of intermolecular forces between the layers. And that will get us both the marks. That's the end of the test. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Let's smash the GCSEs.
You're still here? It's over.